So today we are strapping in for a deep dive into a domain that is, well, it's simultaneously one of the most exciting and one of the most frustrating fields in modern science.
That's a perfect way to put it.
Quantum machine learning, or QML.
It's the ultimate computational hybrid, isn't it?
Oh,
You're taking the vast theoretical power of quantum computing,
mm,
the promise of these exponential speedups for really specific problems like factorization or simulating molecules,
yeah.
and you're trying to blend it with the deeply pragmatic and often messy success of classical machine learning.
Okay, let's unpack this a bit. Before we get too far, let's just be really crisp about the definition. What exactly are we calling QML?
I'd say QML is a computational mission. The goal is to leverage unique quantum resources, things like superposition, entanglement, all happening on a quantum processor to solve standard learning problems.
And that covers the whole gamut, right? Optimization, supervised, unsupervised.
The whole thing, supervised, unsupervised learning, even reinforcement learning.
So our mission in this deep dive is to really map that landscape for you. We want to try and cut through some of the hype and separate the firm theoretical guarantees from the practical applications.
And figure out where the real verifiable benefits are right now.
Exactly. Because QML, it feels so modern, so cutting edge, but the core ideas, they're not actually brand new, are they?
Not at all. I mean, we're talking about concepts that date all the way back to the quantum perceptron model in 1994. The ideas have been percolating for decades.
So what's changed?
The hardware. The hardware's only recently started to catch up, making some of these applications at least feasible to try across finance, quantum chemistry, material science.
But that history, combined with the new hardware, it sort of creates this core conflict that seems to drive the entire field.
Precisely. The central question is the progress we're seeing today a reflection of some intrinsic fundamental computational power? Or is it? Is it just enthusiasm from mashing together two of the most visible and well-funded fields in tech?
ML and quantum computing.
And we have really strong contrasting evidence. On one hand, QML has given us measurable, concrete wins for handling data that is already what we call quantum data.
Okay.
But when you try to apply it to everyday classical data, QML frequently runs straight into these fundamental barriers. We're talking about restrictive no-go theorems and problems that have been dubbed dequantization.
That sounds like a huge tension we need to explore. But I think to understand why the quantum approach sometimes struggles, we have to start in the classical world.
We have to.
We have to anchor ourselves in how classical ML even defines learning. And that means looking at the probably approximately correct framework, or PAC.
Right. The PAC framework is our theoretical bedrock for success. At its simplest, learning is just finding a set of rules, a hypothesis, that successfully connects your inputs to your outputs. And during training, all you're trying to do is minimize the error on your training data.
That makes perfect sense. But the crucial part, the thing that makes it actual learning, is that it doesn't stop at just doing well on the training data.
Correct. The model's true success isn't measured by how well it memorized the examples you showed it. It's measured by its generalization error.
How well it does on new stuff.
Exactly. How accurately can it predict new, unseen data from the same source? If it fails on new data, it doesn't learn anything. It's just memorized.
And this leads us straight to the Vapnik-Sherveninkis theory, or VC theory, which sort of gives us the guardrails for this. How do we make sure a model that learns well also generalizes well?
VC theory gives us this balancing act, the gap between your training error and your true real-world error. That generalization gap, it's controlled by two things: how much data you have and the model's capacity.
And that capacity is measured by the VC dimension. That's a measure of complexity, right?
It's exactly that. It's a measure of how flexible or powerful your model is, how many different problems it can solve. And the takeaway is this: to guarantee good generalization, your model's complexity has to be relatively small compared to the amount of data you have.
Otherwise, it just memorizes the noise.
It just memorizes the noise. It's called overfitting, and it's what's captured by the famous no free lunch result.
Okay, let's make this really concrete with that simple toy problem from the sources. Imagine a one-dimensional classification task. You've got a line, and a central segment is class A, and two outer segments are class B.
Right. And if you try to use a simple linear classifier on that, just a single line, it fails instantly.
Yeah, you can't do it.
You can't draw a single point to separate those three segments correctly. The problem is that the classes are not linearly separable in that 1D space.
So what's the classical workaround? This is the elegant solution that really defines so much of modern ML.
You transform the data, You take that 1D input and you map it into a higher dimensional space, maybe 2D, maybe 3D,
A feature space.
a feature space. And in this new higher space, the data points that were all tangled up in 1D suddenly become cleanly separated. You can just draw a flat plane, a hyperplane, to separate them perfectly. That's the whole point of a feature map.
And that's the core concept. Algorithms like support vector machines can even do this implicitly with the kernel trick, right? They don't even have to calculate the new features.
Exactly. The essential nugget to take away is this. Classical learning often hinges on mapping data into a high-dimensional feeder space to find linear separability.
Okay, so here is where it gets really interesting. If classical ML uses these feature maps to boost its power, how does the most popular quantum approach today, variational QML, try to take this to the next level?
Right, VQML is the workhorse for our current NISQ noisy intermediate scale quantum devices. It's a hybrid quantum classical pipeline.
Okay, so how does it work?
First, you take your classical data, pixel values, whatever, and you embed it into a quantum state. This is usually done by using the classical features as the rotation angles for quantum gates.
So the data now is the quantum state, in a sense?
Exactly. Then a parameterized quantum circuit, or PQC, people also call it a quantum neural network, or QNN, it processes that state. This circuit has tunable gates that we need to optimize.
And then you measure.
You measure. That gives you an expectation value, and that value gets fed back to a classical computer, a classical optimizer, that tunes the parameters to try and minimize the loss.
So the quantum system itself, just by existing in this enormous Hilbert space,
Yeah.
is acting as a potentially exponentially powerful feature map.
That is the promise. And we can go right back to that 1D toy problem. If we use angle rotation encoding on a single qubit, that one-dimensional input gets non-linearly mapped onto the three-dimensional block sphere.
And on the sphere.
On the block sphere, suddenly a classifying plane exists. The quantum hardware is implicitly engineering the complex features you need.
I saw a really cool detail in there about data re-uploading. So instead of encoding the data just once at the beginning, you can alternate between data encoding layers and these parameterized circuit layers.
That's a key insight, and it's borrowed directly from deep classical neural networks. It essentially allows a single qubit to achieve universal approximation power, kind of like how adding more layers increases the power of a classical network.
But there's always a but.
There's always a but. All of this promise runs headfirst into the primary limitation of scaling VQML, barren plateaus.
That sounds extremely serious. Can you just simplify what a barren plateau actually means for training one of these QML models?
It's catastrophic for scalability. Barren plateaus mean that as you increase the size of your quantum circuit, as you add more qubits, the landscape of your loss function becomes overwhelmingly flat.
Flat.
Totally flat. The gradients, which are the signals that tell your optimizer where to step, they vanish. And they don't just vanish, they vanish exponentially quickly with the number of qubits.
Wait, if the gradients vanish exponentially, what does that mean in practical terms? How do you train it?
You can't, not at scale. Remember, quantum measurements always have shot noise. They're just estimates. So you need an exponential number of measurement shots just to distinguish the tiny vanishing signal of the true gradient from the background noise.
So training becomes impossible for any reasonably large system.
Exactly. It's the ultimate scalability wall. The hardware might be able to handle 100 qubits someday, but the training algorithm itself just breaks down long before that.
Which leads to this troubling trade-off warning we saw in the sources.
Yes. A lot of the techniques that have been proposed to get around barren plateaus, things like restricting entanglement or using special initializations, they often inadvertently force the model into a small corner of the Hilbert space that a classical computer can simulate efficiently.
So you solve the training problem by losing the quantumness.
Do you lose the quantum advantage? It's an effective dequantization of your own model.
And even if you could solve that, there's a huge practical time cost to just calculating the gradients, isn't there?
Absolutely. In classical deep learning, you have backpropagation, which is incredibly efficient. You get all your gradients in basically one go. But in QML, we can't do that. We use something called the parameter shift rule.
Which is much slower.
Much slower. It requires a number of circuit evaluations equal to the number of parameters you have every single time you want the gradient. For a QNN with thousands of parameters, that runtime cost becomes completely prohibitive.
Okay, so given these pretty serious walls facing the modern variational methods, maybe the answer wasn't in this hybrid approach. Maybe it was in the pure old-school quantum algorithms that promise those truly exponential speedups.
Right. Let's look back at what you could call the golden era in the mid-2010s. This is when huge claims were being made for things like quantum PCA and quantum recommendation systems.
And these were all based on these incredibly powerful quantum linear algebra subroutines.
They were. The two big ones were quantum phase estimation, or QPE, which can find eigenvalues of an operator with a time cost that scales only logarithmically with the system size.
And the really famous one, the HHL algorithm.
HHL. It solves the quantum linear systems problem. And theoretically, it offered an exponential speed up in the size of the matrix compared to the best classical methods. I mean, this was revolutionary. It looked like the key to unlocking massive data analysis problems.
There it is again, there's a massive catch. One single non-trivial assumption underlying all of these claimed exponential speedups.
The catch. The single biggest assumption in quantum computing for classical data is the ability to efficiently load that classical data into a quantum superposition. This usually requires a conceptual hypothetical device called QRAM.
Quantum random access memory.
Quantum random access memory. And it's basically a superpowered database lookup. It lets you access a massive data set in logarithmic time, not linear time.
An insane speedup that is purely theoretical right now.
Purely theoretical. But if you assume you have it, then algorithms like the quantum recommendation system, or QRS, show these amazing theoretical runtimes. It was projected to be exponentially faster than any classical counterpart.
And this is where we hit the dequantization knockout. So what happened? What was the finding?
The finding was, it was crucial. Subsequent research showed that those exponential speedups were entirely dependent on the strength of that QRAM assumption. The question that was asked was, what if a classical algorithm was given an analogous power to access the data quickly?
So level the playing field on data access.
Leveled the playing field. And when they did that, when classical algorithms were granted analogous high-powered query access, the supposed exponential quantum advantage it vanished. Or it shrunk to be, at most, polynomial.
Wait, so the advantage wasn't physical, it was an artifact of how the data was fed to the machine.
That's the real insight.
Yeah.
The speed-up was mostly a factor of the quantum algorithm getting to use a fictional, super-efficient input method that the classical algorithm, by convention, wasn't allowed to use. Once you remove that unfair advantage, the exponential speed-up evaporates.
It's like the law of conservation of weirdness. An exponential separation only seems to pop up if the problem is either superstructured or relies on a resource assumption like QRAM that's, well, currently impractical.
That's a great way to think about it.
So if QML for classical data runs into barren plateaus on one side and QRAM dependency on the other, where does it actually deliver? The answer seems to be quantum for quantum.
Yes. When the data itself is intrinsically actual quantum states, or quantum processes, this is where QML offers provable and practical wins that are being used in labs today.
This is the real aha moment in the research, isn't it?
It really is. Let's just compare two ways of learning an unknown quantum state. If you try to do full tomography, meaning you try to reconstruct the entire state to predict every possible measurement, it requires an exponentially large number of samples. It becomes impossible for more than a handful of qubits.
But if we change the definition of learning to be more like the Pei-Paget framework, where we only want to predict most measurement outcomes from some distribution,
then the sample complexity just plummets. It drops exponentially. Pax-Par, learning a generic state, only requires a number of samples that scales linearly with the number of qubits. That is a massive, proven reduction in the data you need to collect.
the time to process it might still be high, but the amount of data you need from your experiment is fundamentally less.
Fundamentally less. And for certain structured states, like a non-entangled product state, the problem becomes efficiently solvable in both time and samples.
And this quantum for quantum approach has led to really practical tools like classical shadows.
Classical shadows are fascinating. They're being used right now. It's a very elegant way to estimate specific properties of a state, what we call observables, without having to do that expensive full tomography.
So how does it work, briefly?
You apply a random measurement to your state, and you measure the result. You do this over and over, collecting snapshots. The magic is that to estimate many properties at once, the number of samples you need only depends on how local those properties are.
So if I want to measure something that only involves, say, 3 qubits out of 100,
then your sample cost scales with that number 3, not the full 100. It's an incredibly efficient way to get the information you need about low-bodiness observables.
Okay, so this brings us toward a conclusion. We've mapped these two broad approaches to QML for classical data, and both of them seem to have hit these pretty fundamental limitations.
That's right. The first approach, built from the best quantum algorithms like HHL, hit the dequantization roadblock because of its reliance on QRAM. The second, built from the best classical ideas, the variational methods, are hampered by barren plateaus and other scalability issues.
And that's why the most robust area of research today seems to be focused on these simpler, more interpretable pipelines that target the clear success story.
QML works best when the data is quantum, or when the problem is inherently quantum.
So the final question is, can those physically grounded quantum advantages be useful for classical applications at all? And that leads to our final provocative thought, which connects QML principles to quantum sensing, to metrology.
Sensing is, at its heart, a learning task. You're using a quantum probe, maybe an entangled spin system, to learn an unknown property of the environments, like a magnetic field strength.
Right. And unlike the computational problems we discussed, where the QREM assumption was this kind of artificial resource that led to dequantization, in sensing, the key advantage is metrological. It's real.
It's very real. By leveraging entanglement in your probe state, QML concepts can help us design experiments that achieve the ultimate limit of precision, the Heisenberg limit.
Which means your measurement error goes down much, much faster as you repeat the experiment.
It means the error scales quadratically faster with the resources you use compared to the standard quantum limit. And that's a real, physically grounded resource advantage entanglement, not a hypothetical memory device.
And that shift from chasing a computational advantage that proved to be elusive to achieving a metrological advantage that uses a proven physical resource. That shows that QML principles are already reshaping how we extract information efficiently in the physical world, even if the final answer is just a classical number.
It forces us to embrace this discipline. We have to separate the signal from the hype, we have to prefer clear assumptions, and we have to follow the evidence wherever it leads.
That is a fantastic way to end this deep dive. Thank you for mapping this incredibly complex and exciting terrain for us.
My pleasure.
And thank you, the listener, for joining us on the deep dive.